Hi, y'all, and welcome to episode 3 of the Unveiling STEM Careers That Inspire series. I'm Sandra D., the Community Psych Librarian, and I'm excited to have various STEM professionals here to share their journeys in hopes of inspiring students to consider the excitement and possibility of STEM-related educational programs and careers. Today, we welcome Alex, an electrical engineer who is a defense contractor in San Antonio, Texas. Alex, we are so excited to have you here today, and we can't wait to hear all about your journey. Please take it away.
Thank you, Sandra. Hi, my name's Alexis Gomez. Some people call me Alex, and I'm here to share my story with you. So I categorize my presentation into three different sections: my personal introduction, my professional introduction, and finally my job description as an electrical engineer. So let's begin. So for my personal introduction, I am an only child, and that led to a lot of pets throughout my years. I am 22, by the way. And currently, I have a bird named Wanda, a target dog named Sputnik, a cat named Luna, and you can see a picture of the same cat, but four different iterations in the bottom named Fluffy. She was with me since seventh grade, and she was very important. She almost made it through my whole college career. Sadly, she passed away last year. But apart from that, some of my hobbies are ping pong, love playing ping pong, and tennis, trying to get back into it, and of course, play some video games on the side. I used to play in high school Rainbow Six Siege ESL tournaments, and currently I play For Honor in Warframe. I am from Eagle Pass, Texas, which is a very small border town where you're able to drive to Mexico within 7 minutes, and you can even walk there in 15 minutes, just cross the bridge. I am class of 2020, and that's basically it. That's who I am. So for my professional introduction, I know it's a lot in this slide, a lot to digest, but bear with me. I'm going to just highlight what's very important regarding to my advice to you. So for starters, I received a Bachelor's of Science in Electrical Engineering from the University of Texas at San Antonio, or UTSA for short. In fact, I graduated this year of May, and I specialize in quantum computation, cryptography, image processing, and signal processing. In the last 2 years of my undergraduate career, which are my junior and my senior year, I developed two publications, two conference papers, which I presented at the SPIE Defense and Commercial Sensing Conference. And I was awarded the Best Paper Award for one of them. So I'm pretty happy about it. And all of this happened in 2 years. And it only happened because I finally grew the courage to ask my professor a lot of questions regarding like signal processing, like what if I process an image in this way, and sort of, and so on and so on. And then I asked him about research. A lot of things that I did not know came from just asking a lot of questions. Usually, some people think that asking questions is tedious, bad, annoying, but frankly, at university, those professors are very, very eager to help you, and they are there for you. Thankfully, my professor, Dr. Artyom Gregorian, basically spoon-fed me the material because TSA did not teach this. There was no class for it, so my key takeaway from this slide is ask about research. Ask the questions that you have to your professors because more than likely they were in the same place as you. Right now, I see the math in these papers. I'm like, oh, yeah, easy math, baby math. But when I started, it took me months to even understand what the first page of the right-hand paper is doing. So we all start somewhere. All you have to do is literally just ask. The worst that can happen is they defer you to another professor that's actually will be able to help you. So that's part one of my professional introduction. I do have a second introduction part. So here I talk about mostly what I did during my undergraduate career, specifically my sophomore and junior year. I was part of a NASA Minds group, which stands for Minority Innovative New Designs for Space. Basically, any university, not just UTSA, if you get a group of STEM related professions or degrees. For me, it was mechanical engineers, computer scientists, electrical engineers, even some physicists. And you're supposed to find a solution to a problem that NASA outlines that they currently have in space. If you, for some reason, find a very, very good solution that they like, and you compete with other people with it, and you win the competition, NASA will literally take you to Houston. They will either fly you out, take you there, and you will see your solution being implemented firsthand, either through an internship or probably giving you a full-time position as well. And of course, there's monetary price to it. You get a lump sum distributed amongst your team members. And for this, we chose to do a rover that's supposed to map out the caves of the moon, shoot a laser to different lava tubes or rocks to find very scarce minerals, such as iron or whatever is in the moon. I don't know anything about that part because that was the physics part to do the laser part. For me, I focus more on the power electronics and the image processing, like how are we going to move the rover, how are we going to power it, how is it going to see its environment and stuff like that. That's why you have the image over here at the right with the preliminary design review. We use a 360 rotating LiDAR. And with that, we were able to map a roadway to see like how the rover would maneuver, find the optimal path. So also what I included here was the technical proficiency. Not really here to show off about the technical proficiency, but it's more like if you were to consider any of you going to a STEM related profession, specifically engineering and electrical engineering, MATLAB and for electrical engineering, Cadence and OrCAD suite, which your university will give you for free if you go, and C++ are very important to know for not only for school, but more for a job, especially C++ and the OrCAD suite. Because in college, I was only taught MATLAB in the suite, but no C++. So the difference between MATLAB and C++, just a short, very small overview, is MATLAB is used for prototyping. See it as an iPad, we can just draw whatever. You can actually just you do a 3D cube, and C++ as the hardware, the 3D printer where you actually implement your design. C++ here, think about tracking a plane. Let's say there's a plane happening here, you use radar to track it. You can implement this easily in MATLAB through simulation, but if you want to implement it in a real life application with like physical hardware, C++, you need to do it. You need to know C++. It's industry standard. Of course, there's one thing also, a lot of engineers, especially electrical, are very close to computer science. So you'll be programming a lot because you need to be able to implement your algorithms. So things like GitHub, GitLab, for version control, very helpful. I strongly advise if you're like into programming right now, try looking into those things, those languages, C++, Python, MATLAB, C. You can use experiment, just drink it with it, nothing too advanced, just get comfortable with it. And for my professional experience, which is in the bottom right, as I said, I do signal processing. This is more of a transition to the other slide where I talk about my job description. But as you can see the image at the left, those are actually over the horizon radar forms that bounce off the ionosphere and are able to travel around the globe, depending on the frequency, of course. And so this is mostly used for defense, but this is for the second slide, for the following slide. So for the job description, like I said, I do communications, radar, over the horizon radar, and sometimes image processing, I'm not gonna lie. Well, image processing, just two-dimensional signals. In engineering, you will encounter three different types of industry. In my opinion, you have defense, which is what I'm part in, the medical industry, which self-explanatory, for example, like making a heart or something, an implant, or detecting when someone's about to collapse. That's another issue, it's signal processing. And then finally, audio and image, you can, and artificial intelligence, you can think about this as like Bose, AirPods with their noise cancellation, image processing. Imagine like a Tesla just using AI and image processing to detect if there's a car, what is what, and stuff like that. So for me, I'm mostly going to go into, of course, the defense side since I'm more familiar with it. So for me, in my job description, I have to be able to know different radar communication waveforms in order to extract important, I guess, information of it. The reason why I say I guess is because we don't know what the waveform has. Basically, you're going to be working with a lot of Well, not a lot of, but very little information and a lot of assumptions. So your job will be to extrapolate such data with either very little or no assumptions at all. Also, you of course have to implement algorithms, work with signal engineers to actually implement and deploy these algorithms. And these algorithms, these solutions have to be compliant with whatever your client wants. For example, let's say your client wants to locate again a plane, but or locate a target, but they don't care to identify what type of target it is, what type of plane it is. You can use very much cheaper yet still integral hardware to actually just track the plane. Because if you were to use a higher frequency in order to identify what type of plane it is, it will cost more money. So you have to know what your client wants, and of course, stay within budget. Of course, also you will have to go through a lot of iterations, a lot of testing, validation, a lot of research. Currently, one of the solutions I'm working with for the last 2 months, conservatively, I've been through 40 different iterations of my solution. And trust me, it's frustrating, but I got there. Got there. We finally found a solution. So it's a lot of going back to what I said is just keep on pushing, keep on asking questions, and here at your job, just keep on not giving up. That's usually the nature of research. You have to keep on trying until you find a solution because you will find one eventually. But one other very important thing about defense is you will most likely handle classified and compartmented unclassified information, or CUI for short. This is because for me, most likely it is the communication waveforms, like the frequency specifications, parameters they use that cannot be known to the general public. And unclassified information is just basically very protected information you don't need a clearance for, and that is very regulated by your company. I'm pretty sure Lockheed Martin, any other defense, NASA does this as well, I'm pretty sure. And what else am I missing? And for the medical, for sure, some of it might be there too. And then when you go to AI, right, like Tesla and stuff like that, it's going to be more like, trade secrets and stuff like that. But you will be working with very important information. So that's basically it for my job description. At the right, I have a block diagram that if you were to go the electrical engineering route, signal processing to be precise, you will understand this in 4 years. When your senior year or even junior year, you're advanced. It seems like a lot, but basically it's a car that sends a continuous wave radar around its environment to detect whether objects are present. It does this by using the Doppler shift to find the shift in frequency, and from there you can gauge the distance of how it is for a car. This is mostly used for designing like self-driving cars or those parking assists whenever you reverse and you hear a beep beep beep. That's what it's doing. It's using the Doppler shift. It's trying to figure out the location, how close it is to the car. And then the bottom, the CUI thing, that's what you most likely see in front of either stickers on laptops, on paperwork, saying like, hey, this is very compartmented unclassified information, protect it. Do not like be very strict with it. You can copy it, whatever. You have to get very big chain of approval. But yeah, that's basically it. Thank you so much. Just a little rundown. Do not be afraid to ask questions. Please do not reach out to your professors. Most likely you'll be working with them as you go throughout the years. Those are subject matter experts in their field. So you will see them in the last 2 or 3 years of your college career, regardless of which major you choose. So ask them for research, get acquainted with them, go to office hours. And for job searching, I didn't start job searching into my senior year. You should start doing that your junior year, from what I've learned, even if it's internships. Internships usually lead into jobs from what my friends have gone through, not me. I should have done that, but be persistent. I applied 20 times to the place where I worked and I got rejected 19 times. So applied to different places as well, but still got rejected. So consistency is key. Just ask and just don't give up. So from there, again, thank you so much, and I'll leave you back with Sandra.
Oh, thank you so much, Alex, for sharing your amazing journey with us to becoming an electrical engineer. It was just so much great information that you provided. Of course, there's so many questions that I'm sure people are thinking of and are popping into their minds. I know one of mine was that I think it's so cool that you had so many minors that you were specializing in. And you did say one that I wish you could tell us just a little bit more about. You mentioned that you specialized in quantum computation. Can you tell us a little bit more about that?
Yeah, so essentially when computers first started getting programmed, like before they were the size of our phone, they were huge computer size of rooms, and people had to program them looking like using like paper-like scantrons where they would put holes. I was in there. I'm 22. I was in there for that. I just know about it, right? But essentially, that's happening again with quantum computers. I'm pretty sure you guys heard about it. Quantum nowadays is a buzzword, but my quantum computation work is basically all the algorithms that we use right now for classical computers, which is a computer that you're using right now, the computer on your phone. It's it, it is used for basically like audio processing, image processing. Essential tasks are not able to be realizable in quantum computers. So my research is to try to bridge that gap, try to translate it from our computers to the new wave of computers, basically programming them. And hopefully one day, because quantum computers are not, they're not close to my lifetime. Hopefully my kids will be able to see the work that I provided, sort of like a foundation for those who need to implement already existing algorithms to quantum computers to make their processing even more effective. So that's hopefully answer the question that you asked, but yeah, it's basically what quantum computation is.
I just love that answer that you're working on, basically building the foundation and stepping stone, and I think that's great information for our audience because many of them are students, so, they can maybe think about looking into quantum computation and then just building on everything that the foundation that you're giving everyone, so I just thank you so much for joining us today and sharing everything. Of course, thank you to our audience for joining us for this episode of Unveiling STEM. Please don't forget to subscribe to the Community Psych Librarian channel so that you can get updates on when we upload some other really cool, inspiring stories. And thanks again to Alex for joining us, and thanks to the audience. Y'all take care. Until next time, be well.
Bye.